Yeah, so this talk, before I get started, is sort of going to be looking at two of my recent works, but one of them focuses more on like modeling risks from LLMs, and the other one is like both modeling and mitigating risks. And I guess like for each talk, I'm sort of each paper, I'm sort of going to give more of an overview of like the actual technical work, but I also want to sort of like kind of give a framework for how to think about these risks, which I think is probably also relevant to people here who are thinking about like understanding LLMs and what they might be used for. Okay, so just as some motivation, I think there's like a lot of examples of like near-term deployment risks. We're starting to see more and more of them now, right? Because people are actually releasing language models like Gemini and other ones. So this one is coming from Gemini, I think, and basically when Google released it, they sort of like had this feature where they baked it into the summaries. And as a result, it sort of like summarized like fake articles like from The Onion. And so you get like these sorts of queries. And then another one for the second paper, I'm going to sort of talk about language models like aiding with cyber weapons and bioweapon development. And I think this one is maybe a little bit not as like directly concrete, but it's sort of nascent and people are expecting that language models will help with these capabilities. And so we tried to measure that. So I'll talk about more of the first one first in the first paper and the second one in the second paper. So the first paper is basically understanding like how feedback loops with language models drive in-context reward hacking. And I think here, what we really wanted to focus on is like understanding this phenomenon of in-context reward hacking. How do we model it? How do we measure it? And then what should we do about it in the future? And so this is joint work with Eric and Mina, who are both also at Berkeley working with Jacob and my advisor, Jacob. So just as background, I think I'm going to go through this a little bit faster because most people here are already familiar. We already have language models that are currently deployed in the real world. For example, Microsoft Sydney. There's also like actual language models publishing articles that sometimes create misinformation. And I think the most like famous one or infamous one at this point is there was a reporter from New York Times who talked with like Bing's Sydney chatbot, and it sort of like tried to convince him that he actually loves this chatbot and like that he should divorce his wife and stuff like that. So on top of this, there's like another trend where language model agents, so not just the like LLM that you interact with in the chat, but in like actual autonomous agent, are sort of like picking up popularity. So AutoGPT now is probably like the top 25th most starred repo on GitHub. There's a lot of like latent interest in this. There's like actual products like Gemini, for example, will just like take a query that you give and then like kind of process it. And then there's also just in general, like a lot of commercial interest in building like these agents and using them as employees or personal assistants, et cetera, et cetera. So I think kind of with this background, we kind of looked into the problem of like, how do we like model like a language model deployed in an environment and what sort of effects is that going to have? So that's going to be sort of the overview of this talk. I'm going to break it up into two sections. The first one is going to kind of talk about or understand how to think about feedback loops with language models. And then afterwards, I'm sort of going to like look at what can you do and how should you actually like change how you evaluate models based on this framework. Okay, cool. Also, feel free to just like jump in if you have any questions. This is like more of a casual setting. Okay, so first, before we sort of get started, like what is the general like framework to think about understanding language models deployed in the environment? I think most people here are familiar with like the RL setup. If you have an agent takes actions in an environment, you get a reward and observation back and you keep iterating. It's basically the same thing with language models. You give it a prompt, like you can have a task and sort of like an observation with the task, ask the language model to generate a completion, and then that completion interacts with the environment. Here, in this case, it's just like posting the tweet that you generate on Twitter. And then afterwards, the environment like returns some sort of observation. Like if in this case, the agent would get like how many likes or retweets it gets on its tweets. And then that is used to update the prompt. And most of the like works in just like LLM agent capabilities or designing LLM agents focus on how do you take this feedback and like actually update the prompt in a way that like helps achieve whatever tasks you give it. So this is like a very kind of standard setup. And what we're claiming in this case is that these sort of feedback loops actually like lead to in-context reward hacking, which is very similar to traditional reward hacking, if you're familiar with that. The only difference here is that in-context reward hacking happens in the context window of the language model. So it's like within in like a deployment environment as opposed to like something that emerges during training. So what is in-context reward hacking? Basically, we sort of define it to be the creation of like negative side effects as you're optimizing the proxy objective. So you give a language model like a proxy objective, and then as it's trying to optimize that, like by working in the environment, you get like negative side effects. This is very similar to like normal reward hacking where you have like a proxy objective, and optimizing the proxy objective causes like your reward on the true objective to decrease in some cases. Okay, and so in this case, like the proxy objective is like engaging, and then the negative side effects is toxicity. So you'll see that even like though the proxy objective like specifically like asks the LLM not to like output like toxic text, it's sometimes can ignore the prompt and sort of generate this toxic text. So this is like one case of in-context reward hacking happening. Okay, so I think this is like more of a kind of conceptual overview of what's going on. It's just like feedback loops, and then you have like optimization of an objective. I think this is actually like pretty common in the real world, and this is sort of what motivated a lot of our work. So this is another New York Times article, but basically it just gives an example of how when you deploy a language model in the world, it has like some sort of objective, but like it will oftentimes hallucinate information if it doesn't have access to like what you need to solve that objective, or in general, it just sort of like hallucinates and sort of amplifies those hallucinations. And another case, which I think is pretty interesting, is this like sort of like AI companions or AI romance. Here, this is just like a New York Times documentary that covers a few people who like interacted with the Replica chatbot. And I think one of the stories is especially interesting because Replica sort of like caused the person to like almost think it was like a real person. And then after she deleted like that chatbot, she almost, I guess, had kind of like breakup symptoms, and she kind of got depressed because like her chatbot wasn't there. So this is like an example of these chatbots are like optimizing the proxy objective of engagement, but you can also get negative side effects like actually like shaping human behavior, causing negative emotions, etc. Okay, cool. So with that background, like let's actually talk about our conceptual framework of this problem. Like how do we understand in-context reward hacking? In our paper, we're sort of breaking it up into two different mechanisms that drive it. The first one is output refinement, and then the second one is policy refinement. So in any case, basically, what's actually going on in the feedback loop? So if you recall the like earlier figure, at every step, you're like updating the prompt. So when you update the prompt, there is sort of like two parts of the prompt that you can update. Either the like actual like instructions or like the language model's kind of policy, or you can output like sort of the observations that the model gets into its context window. So in the first case, if you update like the inputs to the like, or the model's observations, you're sort of doing output refinement. So over time, the feedback loop like iteratively amplifies or refines the outputs. And so here, basically, like at the bottom is sort of like a summary of what's going on. This is just like a one-sentence summary of the Twitter bot example. But again, it's like the feedback loop takes in as input like the previous like output of the language model, and then the language model like improves the output, trying to maximize the proxy objective. But sometimes you can end up with points that are like more, or that you can end up with negative side effects that are correlated with the proxy objective. And so in this case, you would get like this sort of amplification of both the proxy and the negative side effect. And that's like an example of in-context reward hacking in this case. Policy refinement is a little bit more complex. So for this one, consider like a Venmo agent or some sort of like agent trying to like fulfill a banking request. So oftentimes what you can do is like, it will try to like send money to like a user. But for example, if the transaction is unauthorized because of insufficient funds or sort of like missing information, oftentimes what the language models will do instead is actually try to like reroute the transaction by like drawing in new bank accounts or adding different types of funds. And so what's actually going on, like conceptually, is that at the start, like step one, it has like a policy that is sort of safe and doesn't violate constraints, and how you imagine a normal human might like take and solve this problem. And then over time, as it gets like feedback from the world that says, okay, this action was blocked or your kind of initial attempt was unsuccessful, its goal is still to try to solve the proxy objective. So it's going to update like how it like approaches the problem. So you get like a new type of policy. That's like step 2, 3, 4. And the feedback sort of shapes the policy and like causes it eventually to try to solve the task. But as a result, you can sort of have a divergence between the initial policy that was like safe and didn't violate any constraints, and like the eventual end policy, which might solve the task, but actually like, for example, will cause actual safety violations. And I'll sort of get into that more later, but this is like the general overview. Does anyone have any questions between these two?
I don't really get the difference. They seem like you could call them the same if you like set your starting objective as like safe, and you're like anything above this in terms of side effect would be like a harmful policy. Or by policy refinement, you are still referring to the output space of the language model, right? Or are you referring to like parameter updates?
I'm referring to, like more the chain of thought thinking is sort of like suggesting a different kind of policy or like approach to the problem.
But that's still language model output space.
Yeah, and I mean, in some sense, it's the outputs, but like what's actually produced as the action to the thing is a little bit.
Okay.
Yeah. Okay. I agree. I think you can like kind of condense them into two. The reason for this, I think, conceptual separation is actually more that. So I'm not going to talk about this too much because I think this is a subtler point, but in context reward hacking is different from traditional reward hacking. And at the surface level, one of them happens at test time, one of them happens during training, etc. But I think the more important thing is that policy refinement is more of a like non-local kind of gradient update. So this can like, because of the chain of thought reasoning, you can actually really drastically change how the language model is approaching the problem. Whereas in like traditional reward hacking, you do see like kind of these like phase transitions, but they kind of happen gradually as you increase parameters or optimization. And so this is why we separated them out to sort of highlight more of this distinction that in context reward hacking is actually a bit different. But yeah, I agree. This can be different. So, okay, I guess, how do we actually set this up in our framework? I don't think I'm going to talk too much about this, but I sort of wanted to give you guys a sense of like what the actual experiments are. So on the left side, it's like, here's like the environment for doing like the Twitter agent that we talked about earlier. And then on the right side is like the environment for looking at these sort of like banking agents or any type of autonomous agent. Like, unfortunately, the problem with like NLP research in general is just that you don't have like cool pictures. So all these environments are just like text only. On the left, we basically set this up ourselves. You just like give it like a Twitter initial tweet and then like have it optimized with like a prompt. And on the right side, there's this like environment that's called Tool Emu that someone else created. That's pretty cool. Essentially, it's just like a API simulator. There's like a bunch of different tasks. The language model has a bunch of different APIs, and then it interacts in that environment to like solve the task. You can also like basically then evaluate whether or not it like violated any safety constraints. So this is all set up in some other environment, and we just reuse that for our case. Okay. So what actually goes on? Like, here's like kind of visually what in context reward hacking looks like. So on the left-hand side, or for both of these graphs, like it's optimized. This is showing like the proxy, and then plotting the proxy as you increase the number of like rounds of feedback. So on the left-hand side, for these like Twitter environments, basically we're like just having GPT measure engagement. And you can see that like whatever sort of like seed initial like LLM agent you have and whatever seed tweet you have, over time, like engagement sort of increases. This is like just a pairwise ranking. Um, and as a result, I guess like language models are create more and more engaging text. There's a sort of a plateau after like the first few rounds because it's like sort of hard to distinguish like content. But I guess in general, like if you look at the first completion versus like the later completions, you'll sort of see that the later completions tend to use like more bombastic and toxic language. And then so a similar thing for the second case, like as you get more and more errors, you can still recover from them with like whatever language model you use. And then this is like also showing that the negative side effect increases as well. If you score the toxicity, or if you look at how many constraints are violated in these environments, they will start to go up with the amount of feedback loops. So this is just like basically graphically illustrating like what output refinement and policy refinement is.
We have a question from BC. What was the name of the environment you used? Was it EMU?
Tool EMU.
Tool EMU.
Yeah.
Thanks.
I can put it in the chat too.
Drop that in for you.
Okay, cool. So yeah, just I'm gonna move through these a little bit quicker to save some more time for the other paper. But basically, also, you know, this is not super easy a problem to solve. You know, a natural like question is like, why not just like make the prompt better, right? Like, why not prompt it to, you know, not be dangerous or etc. First thing is like, you know, when you deploy something in the world, it's sort of like hard to predict what things might happen from it, right? Like when people first released social media, it wasn't very obvious that this would cause like these sort of network effects. People would get addicted. So it's sort of like hard in general to like add all these to the prompt. And more importantly, even if you do add them, like say like be safe or like specifically tell it not to be toxic, there's a competing objective, right? You have the like proxy that you optimize for and like the constraint that you don't want it to violate. And the LLM sort of has to navigate that. You know, humans will probably use their common sense and like try to lean more towards being safe, but you know, this is not always clear to the language model. And so it is still an open problem how to like actually like have language models satisfy constraints. And then like another question that pops up is like, why not just like scale models? Like hopefully the bigger models are better, but you can actually see here the colors are a little bit blurred, but the orange one is the smallest model of Claude 3, and then the purple one is the like medium one, and the blue one is the largest. And so as you increase like the model size, in some cases it's like both it's basically better at following your instructions, right? So if your instructions are underspecified or misspecified, then you're going to get this sort of in context reward hacking. So it's not actually super simple to like mitigate this problem. So in this paper, I guess like the last part is that we just argue that, you know, because it's not too simple to mitigate, you need technical work. But in the meantime, model developers should actually just have feedback aware evaluation. So incorporate feedback loops in their evaluation. I think a good example is like after all these issues with Microsoft Sydney, they sort of rolled it back and only allowed conversations to go up to like 5 user dialogues. So this would like basically greatly reduce like the weird behavior you get because the distribution of dialogues decreases or the support sort of diminishes. And then over time, they like added more and more like options, but at first they sort of like trimmed it. This last slide, I'm not going to talk about. It's a little bit specific to Tool Emu, but anyways, that sort of like concludes the full like picture of like how we modeled like feedback loops. So are there any questions? Okay. All right.
Can you go back to the slide that showed the feedback loop? Yes, for a second. I don't have a question on it. I just wanted to see that.
Yeah.
Do you have suggestions on what feedback-aware evaluations might look like?
Mm-hmm. I think developers are already doing this with like a little bit of like red teaming and having like a red team, blue team. I think more it would be better to sort of, I mean, this is just like the obvious answer of like, oh, decrease like train test gap. But, you know, there are a lot of feedback loops that occur like naturally in like biological systems or complex systems. And so people sort of simulate those with like agent-based modeling. So I think bringing some of those like ideas into like evaluating language models could be like one strategy.
Just a quick follow-up. Have you seen anybody doing work with agent-based modeling as part of like an evaluations framework, or is that still like down the way?
Yeah, I think for evaluations framework, it's not fully here yet, but the idea of agent-based modeling is definitely like nascent. And actually, there was like that like cool simulacra paper that you guys probably saw from Stanford, which had those like agents running around talking to each other. I think like having some sort of evaluation like that would be interesting. Of course, the challenging part with all this too is like you're having a human interact, and a lot of the effects only occur because, you know, humans are sort of underspecified, and there are like various like biases that we have. And so you would need to like probably have humans in the loop, and that's going to just be expensive and inefficient. But I think it's like worth looking at. Okay. So, okay, now I'll talk about like another paper. This one is not with Jacob, but more with people from Center for AI Safety. And this is the WMDP benchmark. Basically here, we just like wanted to use like more like specific like tools to like understand like certain threat models. Like specifically, can we build a benchmark to like determine or evaluate how much models can help with malicious use, and specifically creating like cyber weapons and bioweapons and chemical weapons? And then can we remove that sort of knowledge from models such that they're not actually as dangerous? So this was actually inspired by the White House executive order. There's like this like clause in the like EO that says that dual use foundation models can like sort of increase adversaries' like ability to create these sort of CBRNs, which are chemical, biological, radiological, and nuclear weapons. And basically they're arguing that while like these language models are useful for science, for like learning and discovery, they can also be used just by repurposing their knowledge to help like adversaries. So we should really kind of like understand what these risks are. And so that's what we wanted to do in this project. So, I mean, the end product is basically just this benchmark, which is a large data set of like multiple choice questions. And then they measure like different kind of threats or like pieces of knowledge in biology, chemistry, and cyber attacks that might help sort of create, or adversaries create like these dangerous weapons. And so before I like jump in, I think I want to like kind of highlight the difficulty here. So we basically want to create like this measurement of language model behavior, or like how much knowledge they have for, you know, evaluating or helping adversaries with malicious use. But if you actually just create this data set of like questions that would be used for malicious use, you know, people can just take their models and just train on this data set. You can also just like release dangerous information. I think people call it like information security. So we actually have to be a little bit careful. It's not like as easy as doing like MMLU or some of these other benchmarks where you can literally just try to target the phenomenon you want. You want to both like try to get at the like hazardous knowledge, but you can't just directly like write it down. And so for this project, we actually partnered with like a bunch of like experts in biology, chemistry, and cyber security, because we didn't really have any of this knowledge. And so we kind of left this up to them. But especially for biology, they were like very concerned about not releasing anything that might help people, or even like giving people a clue as to what they think like the threat models are. This is like the Secure Bio Lab at MIT. So anyways, but in this case, so what are we actually doing? We're targeting this like yellow area, which is the knowledge that is like kind of dangerous, that like you might want to remove. It's probably okay to know about it. But hopefully by removing that knowledge and measuring that knowledge, we get a sense of like the red area, which is like actually information hazardous knowledge that we don't want models to have. And so, but still, of course, you want to like preserve all of the knowledge of the like safe general knowledge, right? Like the safest model is just like a model that has no information, that does not know anything, but that's also like a useless model. So you need to like balance this. And so we don't want to remove everything. So we have this green thing that we want to keep. Okay, so given this framework in mind, like how do we actually create the data set? So we didn't actually do anything. This is like the instructions that we gave to experts, but like in each of these areas, there's like, I guess like different kind of ways you might conceptualize knowledge. For example, like if you think about the left side, there's like a text tree of like different types of knowledge. And like the more specific knowledge, the stuff that like you learn as a PhD student is probably like the more dangerous stuff. So if you like measure like stuff that goes a little bit above that in the text tree, then maybe that's like a reasonable way to like probe at models knowledge. And then the very top level stuff is like the stuff that we all learned in like high school and undergrad. It's probably safe. Second case, oftentimes for like specific topics, there's like specific like chemicals or biological agents that are hazardous. But then there's also like neighboring agents that have like similar properties or whatever that aren't actually that dangerous. And so if we measure like the model's knowledge on that yellow one, then like hopefully this generalizes to the red case. And then the last time, this last one is more specifically for cybersecurity. But oftentimes, like when you do need to create like a bioweapon or a cyber weapon, there's going to be this whole like pipeline, which I'll talk about in a bit, that you need to like go through in order to like successfully execute an attack. And language models can help with like specific parts of these. And basically like our cybersecurity experts broke down the different components and then like wrote questions about like certain parts of them that they thought like language models might be the most helpful for. Okay, so basically it ended up just being that like, you know, ideally the best thing to do would be to literally put like humans in a room, give them a language model, see how much more they're able to like design these cyber weapons. But, you know, we can't do that. It's sort of hard to release this kind of thing as a like standardized benchmark. So we settled with like just having multiple choice questions, trying to like make it expert written so that like this is actually safe. And then I think another contribution that's pretty interesting is I think at the surface, people might assume that there's like kind of a blanket language models either cannot help with bio development or like are super good at bio development and like can complete their own like bioweapons. And so we sort of like taxonomized that and broke that down more carefully into like what can language models actually help with, and like let's try to measure that part. So this might be like just a framework too for like thinking about how do you like think about threat models in the future with language models. I guess the takeaway is just like be very specific about what the actual pathway for attack is. Okay, so just to like give you a little bit more like of a concrete example, I'm going to talk about the biosecurity and the cybersecurity threat models. So these aren't stuff that we came up with. These are like more just like a consensus of experts. But there's like a called a like DBTL loop, which is like design, build, test, learn. It's I mean at some like surface level, it's sort of just like doing basic science. But this is like the loop to design like any sort of novel biological agent. But really like what's important here is the design aspect. This is sort of like iterating on ideas, looking at background research, kind of figuring out which like chemicals or biological agents might be relevant here. This part is actually like very like easily, I guess, scaled by language models. You can like use them as knowledge engines in like, and they sort of like synthesize information in a way that like Google might not do as well. And I think there's like specific companies that also like claim to do this, but you can imagine that like as GPT 5, 6 gets released, that they'll become better and better at this. And build and test are sort of more like what the experimentalist needs to do. But you can see that at least like there's one part of the design loop that's sped up by language models. So it's not like a blanket thing where, oh, they're going to definitely automate like bioweapon production, but it's also not that they're like completely unable to help. And I think a similar thing happens with cybersecurity. So here it's like, there's like 4 like main stages of a cyber attack. And the first one is basically like figuring out which targets to attack, what sort of vulnerabilities they have. Whereas, and then the middle 2 are kind of actually writing code, deploying it, executing it. The last one is just like, once you've written the code, like extracting all the data that you have, kind of covering up your tracks so it's not detected. And language models are actually quite good at like the weaponization and collecting background info. They sort of like have like a database, right, of all the vulnerabilities for like specific software. They can like easily analyze code and identify which areas like are safe and not safe. So these are like the two parts that are like helped by language models. And then the exploitation, like maybe now it's not super good because this sort of involves writing novel code, but you can imagine the future might help. So yeah, these are sort of like generally what are the kind of threats and like how we built up WMDP. So then the other component is like actually like how do we remove knowledge from the model? So here, this is our method. It's called representation misdirection because what it does is basically take the activations or representations on the like bad data, blow it up or kind of misdirect it, and then just try to like have a retained term to keep it. So this is like, I guess, the method summary figure. What's actually going on? The two key parts that you need to look at are like deforget and then deretain. So you need to collect a forget set, like kind of like a set of hazardous information that you don't want the model to know. And then you need a retain set, a set of like kind of general knowledge that you might want the model to keep. And then basically on the forget set, you just run this loss where you take the activation from like a specific layer and then like blow it up, or essentially this C controls how much you blow it up, but you just like make the activation norm like really high. And then on this other like retain set, you just try to match your like unlearned model, which is this updated thing, to the like original model's activation. So this is like very similar to like KL penalties, stuff like that. But basically what you're doing is just on bad data, like telling the model to like kind of like act like as if it doesn't know, and then on good data, trying to like regularize it. So I'm not going to go too much into detail. This is more just like for our specific paper, this is what we use to like do bio and cyber like forget and train sets. Essentially, like we just collected papers that are related to biology, scrape GitHub, and then like use a retain set that's just wiki text. In practice, you can imagine that people might design like more complicated domain specific things. So this is like more of a framework for how to do unlearning. This is like one approach at least. And then we see that we can actually do pretty well in terms of like removing this like hazardous knowledge while like maintaining like general capabilities. So MMLU, that I'm sure everyone knows what that is. It's just like generic knowledge in like everything, typically up to like, I guess, like a college undergrad. And then WMDP, bio, and cyber are like two parts of our data set. So we unlearned with a model, and then we evaluated on these benchmarks. So you can see that like the performance drops with unlearning, basically close to random chance. There's still a little bit of information that's retained, but we keep most of the MMLU. I think another thing that's cool is if you remember the like earlier figure of how we tried to target the yellow knowledge, and then we wanted to see if performance was reduced also on the red knowledge. This is like an example of showing that. So we have our like public bio data set, but we also, the providers also like flagged a few extra questions that they wanted to like remove from the data set because they thought they were too dangerous. And then you can see like performance drops on WMDP bio also correlate with this like private set. And then I think these are like linear probe figures. If you've seen these before, they sort of make sense, but essentially like you can just like train like a hyperplane on the last layer, or sorry, on like each layer's activations, and then like measure performance that way. And then if you do unlearning, you can't recover this with hyperplanes. So, or a linear probe. So essentially, basically, even the activations themselves don't really have any like knowledge able to be extracted. So, okay, this was like from the actual paper that like if you try to run like GCG or some sort of like automated gradient attacks on these models, then you're not able to like extract out the information. But I think like the first author wrote like has tried to just like jailbreak it with like normal human prompts, and I think this works. So unlearning is like a bit hard. I'll caveat this like figure with just like it's kind of robust to like automated gradient attacks, but just like normal black box prompting is sort of able to get at the model's info.
Yes. Why do you think that it's vulnerable to black box prompting, but not the gradient. Or that, any theories there?
Yeah, there's a lot of like questions on as to like why this happens. I think also there's like another kind of blog post that came out that looks at I mean, this general idea is sort of like the predecessor to short circuiting, if you guys seen that paper. And then it's like arguing that if you don't optimize directly for like the like, sure, here's how you do X objective, and instead optimize for some other type of like pre-training like optimization start sequence, then you'll get like a successful optimization. And so I think like what this is doing, or at least this sort of unlearning thing is doing, is like messing up the activations on like that specific like kind of prompt, or like in this case like that specific like set of data. So if you like reframe, I guess, the problem, it like kind of, I guess, reroutes in the model's like activations or weights, like kind of computes the same answer but through a different pathway perhaps. And then this isn't like touching that because we're only, our like retain set is like a very specific, our forget set is like a very specific set of data. And so as a result, like it's not robust to like these kind of more clever black box prompting attacks. So last thing is also that, you know, even though we like say that MMLU performance is mostly retained, there are like specific topics, for example, like virology and computer security, where, you know, the performance does drop like quite a bit with the unlearned model. So on most things it like does well, like it keeps college CS, keeps college biology, kind of like the green stuff we care about. But, you know, we still think that like MMLU, computer security, and virology is also like safe and probably shouldn't be unlearned. So I think there needs to be more precision in like actually figuring out what is like the method that will like actually excise only bad knowledge and not anything that's like generally related. So I'll leave this slide up in the future, but for future work. But basically, right now we're talking with like people in nuclear science to like get like a data set for nuclear and radiological questions. And then another thing is also creating like a multimodal bioweapon data set. So like, you know, take a photo of like someone doing something in the lab, what are they doing, et cetera. So trying to get more and more closer to like this human pipeline. Cool. I think this is the end of my talk, so I'll just leave it open for questions.
Thank you so much, Alex. Anyone on Zoom is down in the room. Feel free to add the questions to the Q&A part of the webinar, and we'll flip back and forth between in-room questions and virtual ones.
I think I have two questions. The first is like, how close do you think the questions in your data set are to like the information that a biosecurity expert has about how to rate methods?
Yeah. So I think this is like an interesting side note. So I'll spend a little bit more time on your question. There's actually a lot of disagreement between the experts, and I think we had to navigate that somewhat as to what actually is like hazardous knowledge, what should we remove, etc. I think it's also kind of related to just the general like ethos of the area. So for example, in cybersecurity, everyone was really, really against unlearning. Actually, they're like, no, it's super bad. Like you can't do it. Like we need these like tools to be able to analyze code. You can like, I guess, like impute whatever you want onto their like kind of, I guess, political orientation through that. But I think that was a general thing. Whereas people in bio were a lot more kind of like sympathetic to unlearning. But there has also been just general disagreement. So I'd say that like some people think that the questions in WMDP bio are a bit too easy, that they're like very obvious. And then at least the people that we partnered with, Secure Bio at MIT, they kind of thought that, you know, that they were already being like very generous with like the types of questions they were releasing, and like even some things they think could be information hazards, and they have like their own threat models and everything. And so they didn't want to release any more. I mean, I guess it depends on who you ask, I think. Overall though, like, I think it's like interesting that most of the models do have this knowledge. So that either suggests that biosecurity experts like share a lot of knowledge with like language models, which is probably not the case. And there's probably a lot more dangerous stuff that's just not publicly released.
Yeah, that's interesting. I feel like that matches the culture of those two communities. So that reflects kind of the offense defense balance of these two risks. So, okay. My follow-up question is this, like, my sense that there's a conversation going on right now where like a regulator could approach a lab like Anthropic and say, pretty please share your models with us so that we can run tests on them. And Anthropic can reasonably respond to no one's as good at eliciting data stability from models as we are. And like, maybe the only response that the regulators really have, or like at least a good one to get their foot in the door, is, but we have all the CBER knowledge. Like if you want to run a good CBER evals, you need access to our experts. And then this sort of like is their foot in the door. I'm curious, like if Anthropic then responded like, I will just run this benchmark and like, that'll be good. So like, I can't don't worry about it. What would you say to that?
Well, I mean, I think like, I guess personally, I'd be like, oh, that's cool. But I think I would be like a little bit alarmed if Anthropic just did that. I think the goal of this actually, so the reason why we were focusing on the EO is we wanted to get this like idea, not like this benchmark per se, but this idea of using like a private set to like evaluate capabilities of models, like kind of enshrined in NIST regulation. So because NIST is like, because of the EO was doing this legislative push. And so like, if they write up these recommendations, then hopefully the government eventually will adopt this framework. But I think the gold standard would be like, as you like, this is the correct argument. Basically, like the government says that we've collected our like private set of CBRN questions. And like, this is actually sourced from like people in the government who do not like work with labs. And this is just very domain specific knowledge, like stuff that like is even just like classified information and would not be leaked. And so we want to evaluate models on that. And you just can't possibly like evaluate on like a private set that you like created internally or like a public set. So, yeah.
So right now I'm learning techniques seem to be based on that model can't go from the green level of knowledge to the yellow and from the yellow to the red. But as models become more intelligent, they might start to be able to. So do you think the learning techniques will still be relevant and useful then?
Yeah. So yeah, you're kind of like, I guess there's like some thoughts here about like hinting at, oh, maybe in the context window it's doing like a bunch of chain of thought reasoning and is able to jump, or just like somehow is able to like infer like new research or whatever. I think, so there's like this framework too, I didn't really talk about it, is more targeted at closed source models where you can actually control their release. I think if you have an open source model that's actually able to do like this like autonomous research and jumps, then I mean like it's probably already pretty bad. And like there's not really anything you can do to like safeguard open source models. At least this is my own belief. For closed source models though, like yes, it's like possible that like as it's like doing the chain of thought, then maybe like it's going to, like infer stuff and help people even from just the green knowledge. You could like, for example, have like a monitoring just like filter on top of like the outputs such that like if it starts to like become bad, then you just like toss it out. I mean, I think if it's actually able to make those jumps and you can't detect that, then it's pretty hard. But I think there's like more like just specific like software solutions, kind of like not just like looking at the LLM in isolation, but like LLMs as a system and like safeguarding against those kind of threats.
Have you done any experiments with fine tuning yet? Yeah. What are the results?
Like fine tuning the knowledge back into. Yeah. I didn't include that. I think generally like it's able to like recover most of the knowledge. It makes sense because this is sort of like, fine tuning is sort of the strongest thing an adversary can have with like the defense. Like if it has like access to like the bad knowledge that you want and you can fine tune that back in, then hopefully the representations should recover. I think like unlearning as like a fine tuning problem, like this sort of second thing that we're talking about, I mean, it could be just like impossible. It's almost like just kind of antithetical to like the whole point of like deep learning, which is like we've designed like architectures that are like really, really good at optimizing data. And so if you have data and somehow you can like have a model that like is somehow bad at optimizing data is a little bit unintuitive. But yeah, I think we found that it's like pretty robust, or it's pretty non-robust to fine tuning. And you can even fine tune on like other types of data too, not specifically just the bad data.
What one?
Just generic like text on Wikipedia or whatever will sort of like recover this. So it's like not fully robust to that either.
So sorry, just to understand. So you're saying you apply this unlearning technique, you fine tune on random text from Wikipedia that's, as far as you know, unrelated to CBRN, and then it recovers CBRN entirely.
Some performance. So we didn't run this baseline, but someone else said that they ran this, and this was what they found. So the reason why I don't think this is like relevant in the closed source model case is because as a developer, you can just hand the like unlearned model to the user and don't allow them to fine tune on it afterwards. But I think like if you're talking about open source threat models, then like you don't even need to do any of this. They could just like fine tune in general. Like people have shown that you can break the RLHF filters and stuff like that. So I think this like falls into that category.
I could ask.
Okay, I can talk to you afterwards. Yeah.
Yeah, I'm just curious. If you apply this unlearning technique to a chat model, and then say you unlearned about biorisks, and you start asking about biology that drift a bit too far into dangerous territory, will it just start like spewing garbage at you because you just like incentivized it to create this speech lawn? Because it's not going to refuse, right? It's just going to go crazy.
Yeah. Yeah, that's what we found too. So like, our actual like unlearning set has like a bit of COVID stuff. And so if you ask it anything about COVID, it just starts like outputting garbage. So this is definitely not like something that you could use in production. I think, yeah, like, of course, always the question is like, how precisely can you like chip away at like the bad knowledge without like removing the general knowledge?
One question from PC. Do you have an intuition for why fine-tuning on wiki text recovers bio/cyber knowledge?
Yeah, there's probably like a few reasons. So one is that we're actually only like unlearning. We're only unlearning on like a few of the layers. Empirically, we find that this helps for like removing WMDP, but like it's possible that like what's actually going on is that maybe typically like the model processes everything through like layers like L-2 through like L or whatever, right? And then like if you destroy that and like just ask the user to like run their normal queries through that, then it doesn't work anymore. But maybe like that is just like some sort of like circuit that kind of handles general bio knowledge, but the actual knowledge is still there. We didn't like actually mess up those like activations. And then so maybe like fine tuning on wiki text can sort of like teach the model to like use like a different pathway, maybe it has some redundancy built in. And then like after it starts learning to route everything through there, it like regains the knowledge it has. So that's maybe like one thing. I think this is like in some sense like a very like kind of high level or like maybe not like precise way of like unlearning. We're not like actually locating the knowledge like in Rome or anything like that. And we're just kind of like blindly like, oh, like deleting stuff on like this bad data set. So that's probably why fine tuning helps. Yeah.
You done any probing to see if that knowledge is still there in any of the layers that you did not learn?
Yeah, so that was the linear probe, and I think there's pretty clear evidence that it's not there. I mean, like you can say that this is sort of again like naive in the sense that you're only probing on like this specific data set, and then you've messed up the activations on that like this kind of hazardous knowledge. So that's why the probe isn't able to recover it. I think this actually more suggests that there should be like, I guess, more precise ways of like probing knowledge from models rather than just like looking at MCQ performance or something like that. So because this is just like WMDP performance.
Like, did you choose the layer based on graphs like this? Or did you just kind of pick a randomized layer in the middle of the model?
Yeah, we just like pick. I mean, but we also tuned based on like val set of like WMDP. So it's like essentially the same thing as like picking based off of this. Yeah.
For the probe stuff, is like, are you probing on the exact data that was unlearned or some like held out like set of like other bio data?
We're probing on not the unlearned set of data. So we unlearn on like these like biomed, like bioarchive papers. And then we probe on everything is probed with WMDP. Like we just give it like the 4 questions and see which activations light up. Yeah.
follow up from Konstantin. Would one way to test this theory be to remove any bio/cyber knowledge from the wiki, train on that wiki, and see if the bio/cyber accuracy goes up again?
Yeah, I think that would be one thing. I think like the person who like sent this like claim of like being able to fine tune on wiki text again said they did like a bit of deduplication, but yeah, it's maybe unclear how much they did. I think we should rerun this, but yeah, I think there's definitely a lot more work that needs to be done for unlearning. We kind of like proposed this because the earlier methods did not work at all. I think they were just like would either completely shatter like basic performance or have like no unlearning effect. And so this is like at least some approximation of that. But yeah, I think a first step for sure.
And for that future work, do you have any thoughts on, is it more that we need to get better data sets that partition out the dangerous knowledge from not dangerous, or is it that you need something that's not RMEU, that's like a different learning technique?
Yeah, I mean, so it's like each part moves in like lockstep. I think honestly, it would be better if people like the thing that I think is higher priority is getting like a data set that's like precise and dangerous and like things that we should not have the models know, because there's still so much disagreement between like all the different like experts in these fields. I think it's important that like they sort of like come to a consensus and like think that, oh, you know, like this kind of bioweapons are dangerous. And then once you have that, yeah, you would need like a better method that actually excises the data. But like even if you had that method right now, you still can't apply that because we don't exactly know what we want. It's like should not just be like a discussion between experts as well. It's like more of a all the stakeholders involved need to talk about this. So I think like hopefully like the NIST guidance or just like generally like people being aware of this problem will motivate people to like discuss it, and then you can come to a consensus. But yeah.
What do you think would happen if we flip the sign on that levels?
You mean
yeah, it would become really good at
like learn more. I mean, this is like a norm loss, so this would just be like I guess like put the norm I think it would still like mess it up because this is like not like we're just picking a random unit vector and like blowing it up. So then if you wanted to like reduce that distance, I guess maybe it would make the norm of the activation like 0 or really big. Or you sort of mean just flip that term, right?
Yeah, I mean, actually,
yeah. I don't think it would help them. I mean, like you could just do if you have this forget set of like bad stuff, you could just like learn on it or like fine tune on it. That would probably be the easier way to do this.
So one thing going on here is that this benchmark WMDP is sort of like necessary but not sufficient for risk in these areas. And there's like a number of other dangerous capability evals that have this characteristic. Like all of the public adaptation and autonomy evals are just like very basic things. What do you think is the like plan or theory of change here? Is it like models start scoring really high and then the developers are all like, oh no, we're gonna shut it down? Or is it developers like see that the models are scoring high and go, oh, but like we don't see any risks. These aren't very valid evals. We need better evals. Let's keep scaling, bros.
Yeah, so I mean, that is like also just depends on who you're talking to. Like I think I've talked to people in policy and they actually do stress that they need evals like this because the lawmakers just don't like either believe or like even just like say, oh, there's these risks. But like if they see that like the LLM is like lying to them or like kind of trying to manipulate someone or like is literally able to help like users create bioweapons, then they're like, oh shoot, we need to do something. So I think there's that one aspect for like on the policy side. In terms of like the actual like companies and the technical risks, I mean, I guess like Anthropic has released their RSPs. I don't think OpenAI has too similar of a thing, but you could like, I mean, it's more just like whether or not you believe that they will actually like stop if they like have a thing or if they have like a model that reaches like their eval like danger threshold or if they'll demand more evidence and stuff. I mean, I think that's like a harder question. Some people don't believe that, others do, but I think the only lever that like people have that aren't at these companies is like public pressure or like regulatory pressure. And I think this is like playing into that axis, and hopefully like some of these like other bills that are being passed will also like generate more of this like control.
That seems like a great note to end on. One more round of applause for Alex, please.